the voice. Is the volume okay? Guess the voice is okay. 访客已加入会议。So we will wait maybe 1 or 2 minutes and we will start the class. You want to join online or yes, no. I guess I will start the class slowly, and then see if there's a people who want to join online. So today we'll continue our discussion about content information aspect. So they will basically focus on correlation, information, or content entanglement. So last time we talked about Schmidt decomposition. So this is a method for a state, a quantum state. Right. We are saying there exists some local basis. For example, in A and in B. Right, so we can write down this form. And since this is a matrix, we can do a single value decomposition. So in that perspective, the matrix M can be written as some kind of a diagonal matrix denoted by D, which is a diagonal matrix, delta, and then Uj, delta. So I'm writing reversely. Okay. So if I express this in terms of Mij, right, and then just plug in here, and then you can basically combine this together, and then combine this together. Right. This is for the local space in A, local Hilbert space in B, right? And then you see the index I, which can be sum over 1I, J, which can be sum over 1J, right? So basically indicate you can pull the delta out, and then individually, this is a tensor quantum form, right? And then this is sum over I, or local space in A, this is sum over J, local space in B, right? then the remaining part is the E delta. And this will become delta delta squared. This you just written down. B delta IA is equal J delta JB. And this is a rotation of a local basis in A, rotation of a local basis in B. So this will lead to something we can call this delta A. This is nothing, but so you will somehow rotate this a local Hilbert space in A and B in a way that you can label them in the same indices and with a coefficient. We call it the D, capital D. This is simple. Okay, so we define a number, define the Schmidt number definition. We will say 0, number of non-zero Schmidt non-zero. This is called the Schmidt number. And this is for pure. This is a pure state, right? By finite state. This is a pure state. This is a bipartite. I use this. I can know how many of numbers or how many non-zero values of D by using this Schmidt decomposition, and then the numbers of non-zero D is called Schmidt number. Let me see if there's some audience join online. No. There's no. So now we can define the Schmidt number also for pure state, for mixed state. Okay, so mixed state by definition is defined in the following way: some combinations of rho I, and rho I is the pure state, is coming from some pure state. Also need some of the PI. You can also try to ask about define what is the Schmidt number of this big mixed state, and then the answer is simple. So for each rho I, it's a pure state, right? So we can compute the Schmidt number of each rho I. We can compute the Schmidt number for each pure state. Right. And then the Schmidt number in this case can have different sets, right, for different rho I, and the definition is trying to find the minimum. Which one? So the definition of the mixed state is that we can find the minimum Schmidt number for given for a rho I. And then this is the definition of the mixed state Schmidt number. Now, why Schmidt number is important? Because it's a way to characterize entanglement. We use Schmidt number to characterize entanglement. So, entangled state, for example, we can write something like this one. So it cannot be factorized. Cannot be factorized. Thus, so as we know, this expression is a generic state. So if this is just one component, then it's can written in terms of this one. If it's multi-component, then I cannot rotate this m such that it becomes like this one, right? Rotation corresponds to this Schmidt decomposition. Then we call it entangled state. So if from this definition, then this has Schmidt number. Of course, there's only one non-zero number of Schmidt decomposition because it's already expressed in terms of this form, right? Because they are all diagonal on the same basis, labeled by the psi. So only one non-vanishing one. So the number of non-vanishing one is 1. So we can characterize the entangled state by define the Schmidt number is greater than 1. So this is the thing that you can define. Then we can also talk about something related to local, what is entanglement? Okay. So entanglement in this perspective, showing that this is some kind of local rotation, right? This rotation is unitary rotation. So in this presentation, we find any local presentation, any local rotation cannot rotate an entangled state to a product state. Something we can call this a product state. And then we can characterize entanglement cannot transform to a product state, not transform by local rotation, so it's a unitary transformation indicated by V and U here, or measurements, local measurements. This is some kind of property. So, however, this is vice versa. So in principle, you can make this entangled state by consider a collective of unitary rotation. When I say collective, this must rotate A and B together. Basis. Okay, you cannot do it separately. So this is just a simple fact about the entanglement, and then you can use a very simple way to understand it by consider can it's expressed in terms of this product form or not. And this, if you want to deeply analyze this, you can use this Schmidt decomposition. Now we want to talk about correlation because we want to say something about correlation and entanglement. Right? So correlation. We are saying correlation meaning I consider two things, right? Consider two possible outcomes and asking about these two outcomes they are correlated. So it doesn't really depends on the system is. I mean, it can be defined for a classical system, sure. Right? So I need to have some outcome, and I compare two outcomes, right? So by this perspective, I want to see how these two outcomes correlated or not, I consider some outcome OI and OJ, right? And this is some kind of outcome measured coherently, okay? And then I subtract if I measure this outcome individually and together. I can define this as a correlation between OI and OJ. Okay, so it can be outcome of some of the observable OI. So now we can do more. Suppose I have Alice and Bob, right? So there are two separate subsystems. There's some warning. So we can ask about the experiments they are doing. Right? So the experiments for Alice can have some possible outcome. I denote by small omega, and then it's a set. I can collect all the possible outcome. Consider it's a set. I use this big omega. They have dA omega. dA is outcome. I can do the same thing for Bob. I can measure something, and there's a possible outcome. I denote by lambda. So we can ask about, since I'm consider correlation, right? So I need to consider the joint outcome, the joint possible outcome. So basically, it's collect of two sets. Right? So we can denote this is nothing but this one, and then the set is in this, right? So this is a set of omega I lambda j possible outcome for these two systems. Okay, so this element has a dA element, this dB element is a dA element. So now with this, we can define so-called joint probability distribution. It's a probability for measure the joint outcome. Okay. So we can define a joint probability distribution. So it's a joint outcome distribution. We know by PAB is a probability distribution for a given outcome omega I lambda j, and then we know this is a probability. It's just must in the region 0 and 1, and it must greater than 0. And then we ask about sum over all possible probability. Sum over all possible probability must equals to 1. Right? We can define this probability distribution. Joint probability distribution. Okay. So with this information, we can also know what is the probability distribution of Alice to measure omega I, right? Right. So for Alice measure outcome omega I, the probability must be summing over all other outcomes of Bob's, right, in this joint probability distribution. So this is simple definition. So we can do it vice versa. Right? Do something like this one. This is a simple probability distribution. So we can, with this definition, then we can ask about the correlations. And then it's deeply related to, does the joint probability distribution can be factored into a condition probability distribution or not? And you will see why is the reason. So we can define a condition distribution, probability distribution. When I say condition, meaning there's a conditions for this probability. So in this perspective, let me denote A slash B. So define this way. Suppose the outcome is of this condition is conditioned under the B measured lambda n, for example. This is a condition for A measured omega n and conditioned by B must measure lambda n. Okay, this is the condition. So we define by this format. It's a joint probability distribution, but I need to divide by all possible the possibility of B individually measured lambda n, right? So this is a joint divided by this one. So I can define in the other way around. And this is nothing but the same thing. This is not true. Okay. So obvious is if this condition of A measuring for A measuring omega n is independent of the condition of Bob's outcome, right? Then there must no correlation. So this is very simple idea, right? So if EA is condition probability distribution omega n, or for Alice is independent of what Bob measured. If A measured, the outcome omega n is independent of how B measured, how Bob measured lambda n or n prime. If this equality hold, meaning no correlation, because when Bob measures anything, it doesn't influence what's A's outcome. There's no correlation. This is a simple idea. And then this is must hold for all the n. Sorry, I should use this. And then you can prove if this is true, then the joint probability distribution can be factorized. Because this is just You can prove by the definition. Because these two ways are the same, then PA must be PAB must be PA. So no correlation. Also implies because they can be individually contribute to themselves. There is no correlations in this perspective. Next, I want to introduce some kind of a function or form because it's related to express all these things in terms of the information theory. Okay. So this is just a possible outcome labeled by omega 1, omega n, and omega lambda n. Now we could suppose there is a function. There's a function which depends on the outcome omega I and omega I, right? And I denote this function as some kind of a random variable because this is a set, right? So let's suppose I have a function giving me some variable depends on the omega I, this is the set in here. Then we can ask about this these variables average. Right? So it's some kind of like the expectation value. So we can suppose I have a function depends on my outcome, and then I can ask about the average of this function, right? The average of this random variable. I can ask the average of x. So it's something like expectation value. So it's denote, it can be computed. I consider all the outcome, all the variable x omega I, and then probability of this omega I. This is nothing too fancy. Then since I'm saying this is like just a function, so we can simply express this one is like just an expression. So we can do the same thing for bar. Same for bar. I can denote dy, and then the set is y. This is a function. So for a given outcome lambda I get a value y of lambda, right? And then I can ask about the average of this y of lambda. So this is the average of this y of lambda. So this is nothing but this is very simple. We can define the same thing, and then we can express this as well. Now we can ask about how do I express this average variable of y and x in terms of a joint variable. Right? I can also define a joint variable just like I define a joint outcome here. Right? So first of all, we can write down the joints, we already know the joint probability. This is the condition. We already know the joint probability distribution. And then we already show that we can express in terms of this, in terms of omega and lambda. Now we just need to express in terms of this, using this simplification, right? Because you know this is, let's see this kind of one-to-one correspondence. So we can denote this joint distribution before like this one. This is a different expression of joint probability distribution. So I can get the average joint variable x and y in the same manner. Same manner, so it's a p, x and y, and then have these two outcomes of x and y. This is the same expression. So the average value of the variable x times y. So at the box. So we can ask about what we define the correlation as before for this variable, which is the function of outcome of A and B, denote as a C, x and y. So I can consider this is a joint variable x and y minus each individually and then times them together. So I can define this as a correlation between two random variables x and y. So I'm doing nothing. I'm just trying to provide more structure about this correlation. So before we have a correlation between two possible outcomes. Now let's suppose there's a variable depends on the outcome, and then I can also ask about the correlation of two variable which depends on two outcomes. And then the variable, of course, this setup depends on which outcome you have. So it is easier to define the average variable by averaging out all the outcomes. Right? This is some kind of average now. Okay. And then you can define the correlation between two outcomes x and y. Right? Now let's see what we defined before still works or not. Okay, so if no correlation, then we know the joint probability is factorized to individual, right? That's what we showed before. Then let's see how this affects the correlation between the variables, right? Then we have this one, and then we plug this definition in here. So just plug this definition, pxy, which becomes px, py, right? And then this is x and y. Right? And you see they group to each other. is nothing but E. So by this definition, no correlation which satisfies what we defined before. So this is not surprising. And then we can also try to ask if this is 0, does that indicate this is not correlated as pointing out in terms of the joint probability distribution. So revisely, we can choose the function. This random variable, the function, and then let's make it just like the outcome itself. So it's very easy. This function, let's make it the outcome itself. Then you plug this in here, right? So you plug this in here. Plug this function in here. Okay, so you basically seeing that if you plug this in here, this is a delta and this is delta, right? Then you realize this will be nothing but pxy. And then if I choose in this one and then set this is equals to 0, and this is equals to 0, meaning this exy is equals to ex times ey, and then insert this delta function. This is nothing but px. This is nothing but py. So basically, reversely, you prove this one. Simple. So now we see this is a definition of something like correlation function. I will introduce this because this can be seen as like a correlation function. So we can use this to quantify Alice and Bob. They are correlated. Now, we want to define, this is correlation. Now we want to focus on information. How should I characterize what is the information that's shared by Alice and Bob? How should I do it? This is just a very straightforward definition for correlation because I can define this joint outcome or joint variable depends on outcome. And ask about can it be factorized or not. If it can be factorized, meaning they can individually perform, there's no correlation. If not, there's a correlation. That's how about it? How about the information? How about quantifying the information between and B and above. This is the idea. So we define mutual information. The following way. So I have two possible random variable x and y. I denote this in the and then write this this way. This is the definition of the mutual information. So we want to relate information to the correlation. So as we know, so we should have some property, no correlation. Must be 0, right? So we can first check this one, and it's easy. No correlation indicates the joint probability distribution is vectorized. So obvious this one will give you 0. Now we also want to relate this to what we know more. This is one property. Then 8 to Shannon entropy. Sometimes you can think it's also called information entropy. So as we know from the statistical mechanics, Shannon entropy, by definition, is sum over or some probability distribution x, so px. We want to relate this and this, and you see they are very similar. But this is only one system. You don't consider two. So how should I link this? This is one system. And then I'm now discussing two systems correlation, right? So how this and this corresponds to two systems information. How should I link this to the other? I can do the setup. So if A and B are perfectly correlated, meaning knowing how A also knows B determines B. In other words, the possible outcome in A, if I know, then I know the outcome in B. But if I know the variable in A, the X, I know the variable in Y. Right? So that leaves a condition of this probability distribution. The joint probability distribution, since A and B are perfectly correlated, so I know X, I must know Y. So the probability must be the same if X equals to 1, right? Because I know X, I know Y, I can set them to the same. This part must be 0 otherwise. So you see this is a perfect correlation. And then using this fact, then the two systems correlation or mutual information is already, it can reduce to one system, because knowing one system is equivalent to knowing the other system, since they are perfectly correlated. So you can plug this in the mutual information. So you realize this will reduce to the Shannon entropy. Let's plug in. Because you have log px minus log px minus log px. So you have additional minus term. This minus term. Now I want to introduce more. So this is a mutual information. This is the Shannon entropy, right? And I want to ask about, can we define a condition Shannon entropy with joint Shannon entropy? So we can introduce and then see how it's related to the mutual information, because mutual information has two systems, right? Shannon entropy is one system. So one system, but I can consider there is a condition on the other system that restricts the form of the Shannon entropy. So I can ask about the joint Shannon entropy. Then see how this is related to the mutual information. This is the idea. Okay, so now let's just go to the definition. So let's define the joint. Joint is easy because I just need to replace this by joint. So nothing. Let's replace this by joint probability distribution. Condition. So it's can be considered as a Shannon entropy of system A in A that's conditioned by something in B. So I made a condition. The condition is the B system the random variable will correspond to small y. So with this condition, then I need to replace this by conditional probability, right? So I need to replace this by condition, in this word condition, right? Condition with small y. So this is the condition. So I have a condition that variable must be small. So now we can let's about summing all the conditions in the y variable, right? Which means the measure, the Shannon entropy with condition. So this is a specific condition for the variable fixed to be small y. So if I consider summing all the possible variables defining the condition Shannon entropy, then I need to sum it over all the possible variable in y. So denote as this one. Right. Then just plug in and see what happens. I have two sum x and y. So I have a p x condition with y, right, and the log. This also has a probability, depends on y. I'm defining the condition Shannon entropy, and then I say each individual condition when y, capital Y is fixed to be a small y. has a probability P of 1. So I need to sum over all possible ways times this probability. So I just need to plug this in. This P1. So we have this one. P condition Py. And then as we know, the definition of the condition is the joint divided by Py, right? C, just so this turn on. Right. And then we just need to rewrite this one again as a Px joint probability divided by Py. Right. Then you can basically write this as the joint probability distribution log and then let's compare with this one. There's only one missing. It's almost like a mutual information. So it indicates we can define the condition, the Shannon entropy the other way around, and then make some substitution, and then we will get the relation between the mutual information, condition Shannon entropy, and joint Shannon entropy. So if we do this trick, then we will end up with the mutual information defined this way, right? We just need to trying to split into this kind of format. And then let me do it the following way. So let's do the same thing. I pull out the P joint probability Pxy here, and I log doing the following way. I first keep log P joint divided by Px, right? So I'm missing log Py. This is nothing but this one, right? And then I add log x minus. This is just a part into fancy. So you know this term is this term, and this term that cancel out, right? And you can subtract this one and this one, right? And then you see this one is the condition Shannon entropy, and this one is also the condition Shannon entropy, and the remaining one is the joint Shannon entropy. So if you did out with the joint Shannon entropy minus the condition Shannon entropy. One is the x condition with y, the other is y condition with x. So this is the final expression. So you can consider pictorially, you can have this kind of a region of A and B, and then this corresponds to some kind of Shannon entropy, right? So I can consider this entire region is the joint Shannon entropy. Then I can consider this shaded area is a condition Shannon entropy. This one. It's the condition Shannon entropy. And then this formula showing this triangular area is mutual information. You can interpret the circle I'm drawing is the Shannon entropy for each individual system. This is the interpreters, this form. So let's take a break at this point, and then we will talk quantum system. So everything we discuss at this point is classical system. So we use the probability distribution, outcomes, quantifying correlations, quantifying informations. Next, we will do the quantum version. So let's take maybe 20 minutes breaks. So we'll go back at 3:50. I will just put the bit here.这个标它是指出它这个方程，这方程就是我这个 x 的值一定要等于omega。哦，原本这个是一个方程，那这个地方是一个方程哦 omega 的方，就是说我这边 omega 是一个 set of 所以我每一个 set 都会得到一个 x 到 x。我现在只是说这个 x 必须要等于 omega， 我让这个 random variable 就等于 omega。如果这个东西的话，我就基本上 reduce 新定义的这个那个 average of variable 就变成直接做 outcome average， 因为 variable 就等于 outcome。那我们从 outcome 之间，我们就得到一个结论，没有 correlation。它的 joint probability 就可以直接相乘，所以我们就得到同样的结论。还有之前我没有前面讲的 local 就是说我有 system A 和 B 的，我问说 locally 去转 A 的 degree of freedom 或 locally 转 B 的 degree of freedom， 它是不能增加影片功能，可是我刻画影片功能会变 A。因为你有一个 state apply 等于我们说 generic， 我现在说 local 是指说我 locally 把 I 写成某一个奇怪的 basis UI 新的 basis， 就是一个 rotation 对吧？假设我重新去 rotate 成 k basis， 我这样做到底能不能增加 intent 功能？那我 intent 功能永远是考虑这两个阶段，所以 locally 转做标准。所以你要唯一的 intent 的方法就是在这两个之间同时要转，然后这个等价还要再描述到 m matrix， 就是你可以透过增加纠缠来改变 m matrix。locally 都可以好像在那个基底都没有纠缠。
记得好像，台中大前是好像有一个类似，他就把它抽，这个我也试过，就是慢慢的，反正别人分次，好像找对一个，先积个2次嘛，积2次快疯掉了，然后后来用这方法就是把它拆成62维的，第二维是拆成 x， 然后 ax， 然后去做那个叫抠边，然后把那个然后那这个用新的这个感觉是大家要找哪个？非常健康，我知道，感觉就比较简单。这个我随便一个2次也行。他们在自己去，还有叫你很有进程。我觉得应该没有前面一个的方式下去，前面你因为做，你就考虑的这方面，这是哪个情况？这个好像不是这个，它这个地方，它已经帮你弄好，让你进程。我以为它会有什么，而且矩阵的话，它是有系数的。反正我看到这个就自己上网找人家那种什么，可以找不到，就用找网上，记住这个，这个好像这个位置，而且位置空了，而且我们。这个就考试是期中期末，作业的话这一块有，看看礼拜一次。
Yes, we can start. So this is all about classical. I want to discuss the quantum version of correlation and information. So how should we do it? So we are consider classical system A and B, right? So quantum we can also consider a bipartite system. So for quantum we can express a state or, right? So if you want to relate the quantum to the classical one, the simplest way is interpret the norm or the norm in A for some distribution, probability distribution. So we can define some kind of distribution probability distribution function. By performing projective measurements by defining projector, for example, P. I want to measure I in subsystem A, J in subsystem B. It's nothing but this one. So this is a projector. You can define this way. So you define the probability, the joint probability AB, IJ, right? Because this depends on the local basis I, local basis J. In system A and B, I see the doing this. Because if you will project this state into this specific basis I and J, it will give you the amplitude square, right? Which will give you, corresponds to the probability distribution as we learn from the common physics, right? So once we have this joint probability distribution, then we can ask about the correlation, right? And ask about the correlation. So the simple idea is, if we can define the joint probability distribution in this way, we can also define the individual probability distribution, right? So by the previous classical example, we know no correlation can be defined by knowing this equality holds or not, right? We can use this quantity to define correlation between A and B, and it should apply applicable for the quantum system, right? Because I'm translate this one in this format. Right? However, you realize there's a bizarre situation in quantum system, because quantum system you can have quantum system. You can have infinite choice of the local Hilbert space I at some locations. And then different location, different bases will give you different joint probability distribution, because it depends on the I and J. So in principle, different bases can lead to different results, right? So it seems very hard to characterize correlation or not just by choosing a specific basis. So you need to have a stronger statement for no correlation. So in quantum system, you need a stronger environment for no correlation. Stronger statement is for any choice of the local basis I and J, this whole, then we can safely say it's no correlation. This is one different perspective on that. And then you will find, based on this statement, the product state will lead to no correlation. If the state is a product state, meaning there's only one possible choice of A and B, and no correlation. So with this in mind, then we can ask about correlation functions. Okay. Correlation functions defined for quantum system, we can consider two observable OA and OB. Right? So before we define in a way that we can consider a measure of ON and OB. ON and OB are local operators in A and B. So minus, I measure A only, but I don't measure B, times I measure B only, but I measure. So this is equivalent to the classical version, right? Classical version have two outcome, right? Like the correlation means two joint outcome minus individual outcomes times together. So this outcome in quantum system corresponds to measurement. This is measured outcome. This is a joint measured outcome, and this is each individual joint outcome. So we can use this definition to say correlation. It is correlated or not. So if it is zero, no correlation. No correlation. So it is now zero. Correlated. So this is simple statement. And this can be defined for not just the pure state, but also the mixed state. And we can work on a simple example because we can define operators which has a classical analogy. Then we can compare it to the classical definition. So let's consider the observable OA, as we defined before, is X I A. This is our observable sample B part. J. So plug in this definition. Go back to the original definition because this basically defines as projectors, right? For these two joints one. So you will obviously see this is nothing but right? And then minus each individual one. Then you know this is nothing but the classical definition of the correlation. Because you can basically show if this is zero, then it's imply PAB equals to PA times B. Because you can pull everything out. This is very simple analogy. So as we discussed, we can also define mutual information. So this is the correlation function. I want to define the quantum mutual information. So-called quantum mutual information. So as we discussed before, visual information related to the Shannon entropy, right? So this will relate it to the volume entropy, which is the content. It's defined in a way. It's slightly different than the classical definition. So it's defined in this way. This is known by SE. So defined in the volume entropy rho A plus the volume entropy B minus the volume entropy rho AB. Like this way. So it's slightly different. And then you can show this definition is equivalent to consider a conditional entropy, conditional monument entropy. So it's a two-state. The state denotes by the joint a total system AB, the total system is AB, and this is each individual one. It's a measure of this condition with this. So consider as a condition entropy. We'll define later. We'll define it now. Sorry. We define in the following way. It's a trace the monument entropy defined for reduced or density matrix rho A is defined like we discussed before. Trace rho A log rho A. Right? So this condition of a relative entropy is trace rho A B. It's a total one, right? Rho B A B minus rho A minus rho B. This is the definition. So in principle, and not equals to this vectorized form. It doesn't vectorize, so this is not vanished in general. So this tensor form showing you it can log can be expressed in terms of two terms. This is the first one, and then this is the second one. Right? So it's just like log A times B. And then the other one will be identity. So that's basically you can reduce it in terms of three terms. So the first term here is nothing but minus rho SE rho AB. And then you have second term corresponds to this part, right? And this can be treated as identity trace. B part is 0. We have a plus rho grain entropy. Rho A plus grain the volume entropy. So you can see this. Because this log, this is a vectorized space, the log can act individually. Bit out with individual one before. So you can realize if rho AB is a pure state. So if this is pure, then this is 0, right? The mutual information will be 2 SE rho A. Because we proved this before, if rho A is real, then SA is SE rho A is SE rho B, as we showed before. Okay. So this is basically a very simple introduction about mutual information, and this is just trying to find analogy to the classical system. As we showed before, the classical system, mutual information can relate it to the conditional entropy. Right? So this is just the same spirit, but consider using this definition. Okay. Now I want to change gear to entanglement or correlations in general, or in more like a historical point of view. So as we know, there's a very famous experiment proof that the quantum system is very different than the classical system with indeterminate level. Right? It's called the Bayes inequality. So we'll use Bayes inequality. So that's basically showing why quantum system is very weird. So let's suppose I consider some entangled state. Some entangled state. So it indicates when, so I can, this is some local basis A and B. So L is measure 0, bar must measure 1, vice versa. So this is 1. Vice versa. So you know this is what Einstein also complained about. This is what people know in all the histories. So now what Bell did is Bell want to address this if the quantum system has this spooky actions, no matter how A and B far away to each other, how far away they are, the distance, there's also a spontaneous collapse of the state, or you can have operation that seems best to light if A measures 0, B must measure 1, vice versa. So if you want to address this kind of a system, you need to consider some experiments showing either it's possible or it's impossible. Okay, so we perform some kind of sort experiment. So it's consider the outcome of Alice and Bob. Okay. So Alice has an outcome, 2 outcomes. Okay, denoted by Q and R. And Bob has also 2 outcomes denoted by S and T. This outcome can be either plus or minus 1, plus or minus 1. So it's a simple setup, right? And this simple setup, I can use this outcome to perform what we discussed before, right? What we discussed before is some kind of correlation, right? So we can consider some joint outcome and then ask about what is the combination of all possible joint outcome, right? So I have two operations, each one has 2 outcomes. So I can have 4 different types of joint outcomes, right? So I'm start with 4. So I consider some correlation outcome, outcome related correlation. Correlation outcome. Define find in the Bell's way, which is Q times S plus Q times T, so R times T, R times S plus R times T minus Q times T. So obvious, you can show this is Q plus R times S, and then this is minus Q minus R times T, and then you will show based on the possible outcome here, this either 0 or this 0. If it's not 0, it will be either plus or minus 2, plus or minus 2, right? So and this is plus or minus 1. So all the possible outcome of this combination will only be plus or minus 2. There's no other possible way, right? If I suppose the outcome only have this kind of individually Q and R, SAT only have plus or minus 1. This combination only be plus or minus 1. So this is called the this is the possible outcome of this correlation. And we can consider a joint probability of this measure. This is a measurement of possible outcome. And we are doing some, there's also probability involving, right? So I can ask about and then this is the joint, right? This is a joint outcome, right? So I can ask a joint probability distribution, right? Denotes by joint probability, denotes by P. So I have two possible measure. QR belongs to A, ST belongs to B. Right? I can have this joint probability, and this is the outcome. So I can ask about the measure of this possible outcome, denotes by some expectation value of this QS plus RS plus RT minus QT. Right? And this is nothing but sum over all probability distribution with the outcome you have. So you can sum over all possible probability of the outcome P, Q, R, S, T, and then the outcome either plus or minus 1 denotes by small Q, S plus R, S plus R, T minus Q, T. Right? This is nothing but you can define this way. Right? And then this, as we know, is plus or minus 2, right? And then that's true, and this always greater than 0. So we know, and this sum is always 1. So we know this must less than 2. See, simple. So we find some, again, we find some inequality. So this it's called the SH inequality. So basically, it shows something like this one is less than 2, and this one you can for this possible outcome. And let's see. And this is the very reasonable way you can think, because the outcome is plus or minus 1. There's no other possibility. Right? And then you can, this you can factorize. This is a joint probability, and this is nothing but expectation value of plus T. So you can consider each individual measurement with this combination much less than 2. Now we want to show this inequality basically violates for the quantum system. Yeah, it's not that trivial, right? Because at this one you don't assume it's quantum or not. You just say there is a possible outcome. Right? Outcome is 0. So the quantum system I can also possible outcome 0 and 1. So if you consider quantum system, you will think it should satisfy this inequality. But in real, if you do the real calculation, you realize it violates this inequality. So it's quite surprising. So we can show that it's violate this inequality for this quantum state that we are considered. Let me use up, down, plus, minus, down, up, for example, because I can perform the measurements with possible outcome plus and minus 1. So for Q, I can consider sigma Z. For R, I can consider sigma X. As you know, this quantum state, this square is equals to 1, this square is equals to 1, so the possible outcome is plus minus 1 for this quantum operator. So this outcome satisfies this condition. And for S and the T, I just do the same thing, but with a rotation. And then you know it's also plus and minus 1 rotation. So I just consider this combination. So the outcome for S and T is also plus and minus 1 for a given quantum state. Then we can perform this, right, in terms of quantum state. With a quantum state, this is the expectation value of this joint operator and this joint operator. So we can do the first example. The first example is QS. We can measure this QS for this quantum state, right? So obviously it's just total has a 1/2, and then this is nothing but up, minus up, sandwiched by this sigma Z times sigma X, X up, down, minus down, up. And then this X on the second basis, this X on the first basis. So we can do this very simple. This only give me the sign, right? So this X on this give me plus, this flip the sign. So this will lead to the up, right? And this will flip the sign, so I get a plus, and this will flip the arrow, so down, down, right? And then I sandwich this one. Oh, sorry, I did something wrong here. This is Q times S, because this will be 0. Sigma Z, Q times S, I have a minus sigma Z times sigma Z times minus 1 square root of 2, and then I have a sigma Z times sigma X with positive. So I have this one, right? And as we showed before, this is 0. So I don't need to repeat. This one is nothing, but I pull the entire out. This is plus 1. It doesn't flip the arrow, and minus 1. So I get a minus up, down, and then this is also a minus 1. So total this will be plus, this will be. And then you will see this is the same as this state. So in total you will get. Okay. So it's relatively weird. But because in any combination in this expression, you will never get square root of 2. But in quantum system, you get square root of 2. Okay, you can play the same algebra. Compute RS is equals to, so it will not repeat. You can do it for yourself. So QT. So as a result, if you add all this together, QS plus RS plus RP minus QT, right? You'll get like 2 square root 2. And then as you show this equality is less than 2, so you violate it for this quantum system, quantum state. So why is that? So what's wrong here? What's wrong with the quantum system here? So it's a very, very bizarre case. Where's some what's wrong here? Right. In here we only assume 2 possible outcomes, plus minus 1, 2 different observable. So it's the same setup of what's wrong here. And by this we know this one. So possible statement that is not correct for quantum system is we are assuming this outcome have a definite value even before the measurement. So this is not true. So it's called assuming realism. Meaning outcome plus minus 1 is for plus or minus 1. Outcome must be plus or minus 1 before the measurement. So you know there's a famous realism statement saying that if you don't look up seeing the moon, do you know the moon is there or not? So this is the expression of that statement. So if you don't measure it, moon may not exist, right? So this is basically saying this that the outcome 1 or 0 is not definite before the measurement or quantum state. The other one is the sum of locality. Meaning measurement measure in Alice will not affect measure in bar. So when A do the measurement, it doesn't affect B measurement in B principle for classical system. Because they are far away apart, there's no way they can affect the measure. Right? Now you also need to give up this one for quantum system. This is assumed. So the reason why Bell's inequality can be violated is basically showing one of these must be break. So we can also extend this idea to this is a bipartite, right? We can consider tripartite, three state, three body state. We can do extend it to 3 body state. Okay, so we can define something called a GHZ state in the following way, which is very much like the entangled state I wrote before. Do the same thing, and then you can. It's an extension of this Bell's inequality, so we can do the same trick by consider some measurement So we can define some operator. We notice the following: sigma x times sigma x times sigma x, which I denote as an A operator. The operator is minus y, so I just use shorthand notation, y x. The C operator is minus y, tensor x, tensor y. And the D operator is minus x, tensor y, tensor y. So I can have 4 operators that you can measure these 4 operators by this GHZ state. So expectation value of A will equals to 1, same for B, same for C, same for D. And just showing here using this one. Okay. So okay. So this is a quantum statement. O is what, right? O is operator. Oh. Then let's trying to see if we consider this system as a classical analogy, which local outcome is plus and minus 1. Okay? In the same statement as before, if the local outcome is all plus and minus 1, right? In terms of classical point of view, it's an example trying to show the locality condition. Classical point of view, local operator denoted by x and y. The possible outcome is also plus 1 local one. So we can consider this local operator either plus or minus 1, right? So we can consider depends on the polymetric x, A, depends on the polymetric B, A, X. I denote this is the possible outcome. X is the outcome. Classical outcome, or the outcome. Sorry. If the outcome can be locally split into this form, the local outcome can be split. So the first is this one, which I denote this is the measure of A, which is 1, right? So I can have this table. The second one is minus y. If I locally measure outcome is plus minus 1. This is the local measure outcome. Cx, sorry, which is 1 as well for the state. So locally is also if you times 4 together, the right hand side is 1 because 1 times 4 times 1. And then the right hand side, as you know, this outcome is plus or minus 1. This one outcome is plus or minus 1, so this is plus or minus 1 squared. So this is also plus or minus 1 squared. So this one will be 1, this one will be 1, this one will be 1 as well. So I have 1 on the left hand side, but I have a 3 minus 1. So I get this equality. Okay, so what this shows you is locality must give up. Locality must. Because if you don't give up, if you build up with this conclusion. Locality meaning the local operator give you the definite outcome transformation. Now we want to go back to, okay. Since now we are jumping to the 3 particle state, then we can ask about how do we quantify the entanglement the correlation for tripartite system. So the question now we can ask is, how do we quantify correlation for a tripartite system? So we can define correlation for tripartite system. Saying that if the total density matrix can be vectorized, this has no correlation for sure. I think that if only but if you want to quantify the entanglement for this tripartite system, it will lead into trouble because now we are considered bipartite entanglement. So if we consider how about entanglement? So the question correlation we can define this way. How about because now we just introduced the von Neumann entropy as an entanglement quantity. Right? There's others, but let's suppose we only consider this case for the geometric decomposition. Right? So suppose this system can be vectorized in this way, then we know system AB has no entanglement to system C since they're vectorized in this way. However, there can be entanglement in AB. So it's not easy to quantify multi-partite entanglement as one example because in this case, no entanglement between A, B, and C, but entanglement in A and B. So yeah, so it's hard to express a multi-partite entanglement. This is just an example. Entanglement. And B. So we need to find a way to characterize generic entanglement. So need the new method. To quantify entanglement, generic entanglement. So what we're doing here is we introduce the distance between two states. So we need to find some geometric meaning, try to use geometric meaning. In this perspective, we're using the distance to quantify generic entanglement. Okay. So we want to find the distance, so we can ask about the distance between two states. The psi and the phi example. And then the simple one, we know distance is a value, is a real value. So maybe it's easier to define the distance between two states by using the overlap. So overlap can be a good way to describe distance between two states. So this is a real value. But this is a state, a pure state way to do it. So can we extend it to density matrix? So if this is a density matrix, how can we define the distance? The state we just use overlap matrix. How do we define the overlap between other? So it's defined in so-called fidelity. So I consider the distance between two states, rho and sigma, by taking the trace of square root of this one, and I take the total square. So first, if rho is equal to sigma, meaning they are the same state, right? And as we know, the same state, this is z, this is y. So we should see the similar for this quantity. Then if you see this one, then this they are commute, and then that will becomes rho square, right? Trace of all n density matrix is equivalent to 1, and then 1 square is 1, so we get that sigma. If rho this density matrix is perpendicular, because this is some kind of a summing over of eigenvectors or some basis in the Hilbert space, and this is the other basis. So let's suppose the basis, the summing over basis of this rho is perpendicular to the summing over basis in sigma. Then this must have zero overlap because they are perpendicular, they are orthogonal to each other. So rho is a density matrix, and you consider some of the other basis. So I'm saying this is kind of okay. So when I say they are perpendicular, meaning the span of I and the span of J, they are belong to two orthogonal vectors, set of two orthogonal vectors, right? Such that this must be zero, and to imply this is zero. It's a perfect way to define this format. And then you can also express this as a trace norm, defined as a norm of two. And this of A, by definition, is trace of square roots A, A. It's called trace. So with this definition, then we can characterize entanglement of a tripartite system or multipartite system in the following way. So I can consider a generic tripartite state, psi ABC, and then I can consider non-entangled bipartite state which has a tensor product form. Right. And then I can compare the distance. Right. If this is very entangled, this is non-entangled. Overlap must be zero. Right. So we can use this to quantify their distance. And if they are far away to each other, then, or if they are close to each other, then this must close to the product state, to the non-entangled state. Okay, so we can use this one to characterize entanglement. Okay, denote by EG, which is trying to find alpha defined in the way. I can consider. I want to consider entanglement of this tripartite system, tripartite state. So what I can do is I consider generic non-entangled state alpha. So alpha can be arbitrarily choose local basis, right? Non-entangled state. I can ask about what is the maximum possible fidelity for choosing alpha. This is the definition. I can find the maximum star by choosing the possible maximum alpha of this fidelity. And then fidelity I consider here is a simple example for pure state. The fidelity will reduce to nothing but the overlap square. Okay. So I can have a freedom to choose alpha. I can find the maximum alpha such that this one, the fidelity is the largest, which means this is far away from the non-entangled state. So I can try to find a quantity that's characterized entanglement, since in terms of the largest distance that can away from the non-entangled state. Okay. So it's a very valid way to do this. So it's very natural to define this way, but denote the entanglement using the distance by taking the log of this minus log of this. So characterize the entanglement for this one multiplied by this one log of this f of ABC from alpha. Find this one, and then we can just use this GHZ as we know this is the entangled state as an example. HZ. Let's see what is this outcome. So the maximum fidelity you can find, the alpha you can choose is either 0, 0 or 1, 1, 1, and then you just compute it. This value. This will give you. This will give you basically 2, square root of 2, right? And the square root of 2 squared is 1 over 2. So this will give you log 2. The last thing I want to talk into this lecture is regarding to the purification. So the idea is for a mixed state, we can consider it comes from a pure state by performing partial trace. Okay. So we can do the same thing we know before for a reduced density matrix, which defined by taking the partial trace of rho. Right? And suppose rho is coming from some pure state. Right? If we're performing this partial trace in terms of local basis, it looks like a mixed state. This is in the local basis. Local basis. Okay. Purification meaning I want to add the B degrees of freedom back and then purify this state. So I know what is the corresponding pure state. That means if rho A is a mixed state, I can add additional degrees of freedom. That's denoted by B, right? And then I can expressed in terms of the pure state, which is nothing but if you're doing this, then your mixed state is nothing but taking the partial trace in B of this pure state. Right. Yeah. So you can see this is a purification. You want to back engineer a pure state or a given mixed state. And then you can doing this by attaching a degrees of freedom in B, but B in this expression is relatively arbitrary, right? There's no unique choice because this I alpha is the indices of a local basis. I can use these indices for different bases, and then it will lead to the same mixed state, right? For no unique choice of I in B all lead to the same mixed state. Okay. Equivalently, let's say in this